So I'm good over here.
You're good over there. Not that I need to be recorded, I don't think, but something about being personable. I don't need to be so zoomed in, right? All right, so did you want to talk about things that will help you on homework 5?
5.
Because in homework 5, you start discussing the all-important Taylor's theorem and the remainder theorems, which are going to be important.
I haven't looked into it yet.
You're going to be looking at manifolds more closely, so you can learn about patches. And what else do they do? Let's look.
Taylor's theorem?
Yeah, Taylor's theorem.
Yeah.
And then Lagrange multipliers for more than 2 variables. And in next section, I guess section 7, you go into Taylor's theorem or expansion for a function from like Rn to Rm. So in section 5, all you did was look at, so I don't know where we want to start here. Okay. Okay, so all you're going to do for in section 5 that continues what you did in the previous section is Lagrange multipliers. They only really introduce 2, well, some theoretical stuff. But the only thing they add in is some more variables for your function and possibly multiple constraints. So those are the 2 things we have to deal with. So even if you have a function of more than 1 variable, right, it doesn't matter how many variables. If you want to optimize, so maximize or minimize some function subject to some constraint, say we write it as some function set equal to a constant, so this would be the level set of the function, say 0 even, to make it match the book. It's exactly the same program as before, where you want to find critical points by solving this system. The gradient of f is the multiple, so the multiplier is the Lagrange multiplier. It's just a number. Just to be equal to the lambda, gradient of f is equal to lambda times gradient. And then together with the constraining equation itself, it gives you a system not necessarily easy to solve because it doesn't turn out to be often linear, right? But you're going to solve for critical points and then try to figure out whether you get maxes or mins at the critical points or neither. So there are going to be some examples where they just add in, instead of just x and y, like in the previous homework, they give you x, y, and z. But they also get more abstract. So they'll just give you a function of variables x1 through xn. And you're supposed to use like the whole dot, dot, dot thing where you have to find a pattern. Oh. So here's an example. On your homework, you're doing question 5.8. 5.9 is very similar, so I'll do that one. And after this, we'll look at an example where you have multiple constraints. Right? So here it's still, all that's new is more variables. So this is a 5.9 in the book. I should be more careful. It's section, chapter 2, section 5, right? 5.9 problem. All right. So let me just make sure I read it correctly here. So, did I? Did I press record? All right, so here's a function. And what we're going to do, both in you're going to do in question 5.8, and we're going to do in question 5.9 as well, is to prove what we call the, do you know what arithmetic mean is and geometric mean is?
Arithmetic mean, that's like number of the elements, some elements divided by
The number, it's just your simple average, right?
yeah.
But there's other kinds of averages that are used in different situations. So there's the arithmetic mean, where you is it numbers greater than 1 or just positive? It's just positive, right? Yeah. Yeah, positive numbers. So we're going to try to minimize this function for magical reasons. Well, you probably see where this the average is coming in, right? This is the average of minimize this function subject to the constraint that the product of all the variables minus 1 is 0. That is, say all the product of the coordinates of your points has to be 1. All right. With an additional, we'll just say that we're going to be looking at positive xi's. Now, is it possible that some of the x's are 0?
Sure.
Well, is it possible that some of the x's are 0 if we have to satisfy the constraining equation?
Oh, then no.
Then no, right? Because as soon as one of the coordinates is 0, then the product is 0 and 1 does not equal 0. So the x's we're going to assume are strictly greater than 0. Just because we want to use this to prove the following. So if you take the arithmetic mean of a bunch of positive numbers, or the say geometric mean, so you multiply them, right? And what do? Square them, or do you raise them to the power? Squared, right? You want this to be and you take the nth root. Is it squared? No, if the x's are positive, there's no need to square them. So you're going to have the product of these n positive numbers, and you're going to take the nth root of the product, and that gives you your geometric mean, and that's supposedly going to be smaller than the arithmetic mean. This is ultimately what we're after, this inequality.
And is that assuming all the elements are same in both cases?
Yes, so the x1 is x on one side is the same as x1 on the other, and so forth.
Okay.
So that's geometric mean is less than or equal to the arithmetic mean. All right. Well, we can use the we can start our Lagrange multiplier program here. If we look at the derivative of f with respect to one of the coordinates, say xi, what will that be? You can do like x1 if you're not sure. Differentiating f with respect to x1 is x is 1 divided by n.
And the rest are constant. So, okay.
So that would be 1 divided by n. So you see that the gradient, well, let's get, and then what's the derivative of g with respect to xi? G. So that's a little bit more abstract because it's hard to figure out how to denote that.
That's just everything except x1.
Yeah. So the way we can write that is it's just the product of all these, right? Including xi, if you will, but then we just take out xi. And the notation mathematicians often use, look, it's even in your book. Maybe a professor used it. You take out the xi, so you indicate that it's easier. It's kind of like drawing a hole in the graph of a function, right? You have to indicate the absence somehow. So that just indicates that this is taken out. It's absent, right, from this product. Okay. So now if we used to have a general formula for the partial derivative of f and g, right? So Lagrange says that we should take the gradient of f, so that consists of these partial derivatives, set it equal to lambda times the gradient of g. But this is exactly the same formula you would use regardless of which coordinate you're looking at. So we'll just say that this has to be true for I goes from 1 to n. As opposed to writing this, so I could write it like so, as an alternative. The derivative of f with respect to x1 is equal to a multiple of the derivative of g with respect to x1. The derivative of f with respect to x2 is equal to lambda and then times the derivative of g with respect to x2. So you see how that's a little laborious, right? But you could do that if you're not comfortable realizing this denotes that you actually have n equations right there.
I have a question actually.
Yeah.
I just realized, so the equation that the f is being subject to, that's x1, x2 times xn, all minus 1.
Mm-hmm.
How do we get from there to the geometric mean?
Oh, we'll see. We'll see. All I'm saying is that at the end of the day, this is what we want for positive numbers.
Okay.
This is what we're going to get later.
Okay.
And we're using Lagrange multipliers to accomplish that. Okay. And then together with the constraining equation itself, we get a system of equations. There's n plus 1 equations there. Go ahead and write all of them explicitly. So often when we do Lagrange multipliers, we work with the gradient, part of the Lagrange multiplier program here. And what will this allow? And we somehow try to eliminate the lambda, if you will. So oftentimes that's the strategy to get a relationship between the x's. And once we have a relationship between the xi's, we can come to the constraint to actually solve for some of the x's or maybe all of them. So so we already said that xi cannot be 0, right? So let me do this. So suppose we have xi missing here. Then we have, let's say, x sub j missing here. They could be the same, they could be different. Okay. To compare these more easily, what you can do is you can multiply the first equation by xi and the second equation by xj. Do you see why? I mean, it's not obvious, but do you see why somebody would want to do that? If you multiply the first equation on both sides by xi, you've introduced that factor. Remember, it's not 0, so it's legit. You're not losing information. So you have this product, and then multiply both sides of this equation by x sub j. And where does the magic happen there? Well, now that you've replaced xj here, this factor, and you replaced xi, that's a full product, right? So these are in fact equal.
Oh.
Right, so this tells me that xi divided by n is the same as xj divided by n. That is to say, xi equals xj. And this is for any pair of indices, I and j. So it has to be true for all coordinates. For any ij in the index set for our coordinates here. So this means that x1 has to equal to x2, which has to equal to x3, and so you get that all the coordinates have to equal. So that's what, looking at these n equations, right? Notice how we eliminated lambda, just basically just disappeared, if you will. And so now we have a relationship between the x's, so we can now come to the constraining equation and actually solve for x. So looking at the constraining equation, x2 has to equal to x1, x3 has to equal to x1, xn has to equal to x1.
And that's n times, right? x1 to the n power.
Yeah, that's right. There are n factors here. So obviously x1 has to be, well, depending on whether n is odd or even, right? It could, x1 could be positive 1 or negative 1, but we are looking at x's which are strictly positive because we're specifically looking at this geometric mean, arithmetic mean business. So we're assuming we're working with positive numbers. So x1 would be 1, which makes all the variables 1. So for all the coordinates. Okay. So there we go. We have solved for critical points. It's essentially the critical point. There's one that we care about, and that's where all the coordinates are equal to 1. Okay. Now, then you would want to say, well, at this particular point in the domain, we plug that into our function, what do we get, right? So f at x would just be, add up all the coordinates, there's n terms, so that's just n divided by n, so 1. Right, I'm looking at f here somewhere. So I'm just adding up all the ones. Put a little thing here. Okay. Now, how do we know this is a minimum? How do you know that this is the minimum the function will take? Not a maximum.
We have to conjure up the Hessian.
Well, no, you haven't learned. You've learned a second derivative test when you have just a function that you can find local maxes and mins for without any constraints. So the Hessian is used when it's an unconstrained optimization problem, right? So you don't have any restricting equations like this one. So use the Hessian when it's not Lagrange multiplier, right? Lagrange multiplier, you think is an optimization problem where the inputs cannot just be anything. They have to satisfy some conditions. So it's constrained optimization. Okay. I think there is a test called the border Hessian if you're working with Lagrange multipliers, but I don't think you learned it, so, and I don't even remember it, to be honest. I mean, I don't know. I've seen it. There is a test, but, or we want to minimize this. So how do we know that this is a minimum? Well, what if you take any other point?
Other points. Oh.
Right, like, so we know that if you have your function attains a maximum or minimum, then it has to do it at a critical point. So this is the only critical point. The one that's all ones, right? This is the only critical point we found. So if you take any other point, which is still, still has to satisfy the constraining equation. Because we're only talking about points that satisfy that constraining equation. And if you get something larger, then this cannot be a maximum, right? Because if it, well, it can't be because you find something at a place where the function is larger. If that makes sense.
Can you explain that?
Yeah, let's just so suppose we have x being, say, 2, 1/2, and the rest are ones, right? So there's n minus 2 coordinates here. Not that it matters. And then we have 2 coordinates which are different. Yeah. So let's stick that into the function. So you get 2 plus 1/2, and then plus 1 with itself 8 times. So this is 10 plus 1/2. Oh. Wait a minute, how did I get 8? Oh, n minus 2. I haven't. That is the weirdest thing. Monday. I'll just chalk it up to Monday. So you get 2.5 plus n minus 2 all divided by n. So is that going to be smaller or bigger than 1? Well, let's think about it. This is 2.5.
Yeah.
This is minus 2, so you get 1/2 plus n.
So it'll be larger.
Larger, right. So we found a different point that's still on the level curve, right, of it. So this still satisfies the constraining equation. But where our function has a larger value, the f at x1 is greater than 1. So we know that the function cannot be attaining a minimum. This cannot be a minimum because there are places where the function is bigger. Or so this cannot be a maximum.
Yeah.
Sorry. Oh, I gotta say it for the recording, but it cannot be max because we found a place where the function is bigger. So this must be a minimum, just by elimination, process of elimination. Okay. Okay. There you go.
Is there a scenario where you can't determine whether it's a min or max, like a saddle point?
I guess even I've been doing this for a while, still don't, I guess I've never encountered that.
Oh, I see.
It's hard sometimes, even just if even for unconstrained optimization, we use the Hessian second derivative test. Even then, sometimes that fails, and it's not always easy to see whether you have, right? If the determinant of your Hessian is 0, then the second derivative test is inconclusive.
Yeah.
Right? So you have to use some other means of determining what's happening to your function at the critical points you got. So I don't know. I'm sure it's difficult in general. It's not always obvious. But that's a good question. Okay. All right, so this is a minimum. So we know that f contains a minimum, right? So f at any other point but how do you guarantee that the product is 1? That is so weird. Okay, so let's just say, oh boy, that is. So I guess I should have, yeah, this is fine. So the function at any other point has to be greater than 1. At least a point that's on the curve, on the surface. Satisfies the constraining equation. All right, but what is our function? This is f of x. It's greater than 1.
So you're saying if there's a point that's greater than that particular critical point, then that implies that critical point is a minimum. Something like.
I'm just trying to see, because this should work for all positive numbers. It's weird. How do they define? Okay. So I think I'm missing a step, but I'm definitely missing a step here. I think I have to more creatively define my x's. Let's see. The product is 1. What can I make? How do you define your x's? So let's see. So how can we do this? It's almost there. Well, I might have to redo this then later. Okay. But it's almost there, right? I'll try to fix it, but I'm missing like an n in the denominator. If you take the nth root of both sides, you're going to get the geometric mean on this side. You should be getting the arithmetic mean on the other side. Well, it's not wrong, but how do I define? Okay, define, oh, okay, I think I know. Xi should be AI divided by, yeah, maybe that'll work. The product of all the A's nth root. Okay, so let's see if that satisfies the and that's a minimum. So oh, so it's now it's right. It's one is the minimum for the function. Okay, that was good. So let's see if we multiply these coordinates together. Numerator we get xi, x1, or a1, a2, a3, an, and then you have this denominator in each of these faculty. Oh, jeez, okay, I'm reading messages. So x1, for example, is just a1 divided by this product. Okay. So when you get x1, you get that factor in there, but you have n of those, right? Each of these n coordinates has that denominator. So when you multiply all those denominators, it's the same factor raised to the power n, because there's n of these factors. So that's equal to 1. Okay. So I think this is what we want to do. So then we're going to just notice, and why am I doing that? Why am I checking that this is 1? Well, because if we define our the x's like so, notice they're I'm assuming all the x's, ai's are positive, so xi is positive. And also the product of these is 1 because I checked directly, right? When I replay using this definition, get these. And so because I needed to have a point that's on that satisfies the constraining equation, right? So now we can come back over here. And we have our function at the x's that are defined right here, right? So that would be.
What is a? Is that just value x?
Yeah, so I should have used a here. The x's are just intermediaries. What we want to prove is that if you have positive numbers, so a1 times a2 dot 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 an. This is a1 plus a2 and so on. So the x's are just intermediaries. What I forgot is that, yeah, sure, we get that our function at the point 1, 1, 1 is at least 1, but that doesn't give me the inequality you want, because I can't assume that, because I'm looking just at x's that satisfy the constraining equation. So I had to put an extra conditional on the x's here. So I don't know what I'm saying. Okay, but let's just say that this is the function at x1. Right? X2 and so on. 1 over n. And 5.8 is probably just as easy or as difficult depending on how you look at it. So. Okay, so this is all divided by n, right? So this is at least 1. That's what that says. And there we go, right? We have, if you read the common denominator there, is common, right? So all this stuff you can just multiply through, it's positive as well, so it doesn't change the inequality. Well, that took a long time. Okay, so we're left with just the average of these positive numbers on one side. And that's at least as large as the geometric mean on the other. That's what we wanted to prove. 5.8 is very similar.
So that is the optimization.
Yeah, that's just an application of, it's a Lagrange multiplier example, where you have more than two variables, and it's in the best way more than two variables, it's x1 through xn, so you have to do a little bit more abstract kind of computation. Okay. All right. So
How does that show that it is optimized? But I guess
well, no,
not
no.
really understanding.
Well, so if you have your function attaining a max or a min, it has to be at the one. It has to be at a critical point. So it has to satisfy the Lagrange multiplier system of equations.
Yeah.
So if this weren't a max nor a min, we wouldn't have this as a critical point. So we know we have a max or a min, right?
Oh yeah.
Because then that guarantees that you get a critical point. So
Oh, okay.
is it okay?
So if we get the critical point, that's the max. So the next,
Well, we only had one critical point, right?
yeah.
And we found places where the function is larger.
Oh yeah, yeah. Minimum.
So there's no way that this would be a maximum. It has to be the minimum
Yeah,
function.
my bad. I guess I'm just having trouble trying to relate the constraint with its geometric. What looks like its geometric version.
Yeah, they kind of essentially normalized this somehow, because the function that you want to optimize is just the average of numbers, but the constraining equation kind of looks like it's the beginning of computing the geometric mean, right?
Kind of looks like it.
Except it's normalized, because instead of this this being, like if you raise this to the power 1 over n, depending on what positive numbers x1 through xn are, you don't have to get 1, but they essentially normalized it, right? So that's how they kind of got the constraint. And we see that's easy enough to solve, because if we have this condition for all x's whose product of coordinates is 1, then we can very easily manipulate that and get a statement about all positive numbers, a's. Right? We define the xi in such a fashion so that our constraint is satisfied. So do you want to look at, maybe I should let your professor talk about manifolds. There's just one problem in the homework about finding the manifold. I don't know. If instead you want to go to Taylor polynomial stuff.
I guess I can brush up on manifolds. Yeah, manifolds. I guess using manifolds. Yeah.
All right. So check if anybody's in the chat today. All right.
There's really no one else.
I mean, sometimes they show up. Last time we had 3 people. So do you know loosely speaking, what a manifold is? Have you come across that idea?
I know I learned it, but I don't think I fully understood it.
All right, so a sphere here's, not a solid ball, but just a sphere is a two-dimensional manifold. If I can spell correctly. Okay. The curve is what kind of manifold if you look at this? Let's say we're looking at the graph of y equals x squared. What dimensional manifold is that curve? Would you guess?
One dimensional.
Yeah. I'm not going to try to draw a three-dimensional manifold. Okay. Well, no, I couldn't, but just a solid. Not full of a manifold. All right. So what would make us think, what's the commonality here? Well, for each point on this curve, you can draw a tangent. It's a unique tangent. Okay. And so that's just a line. If you'd like to think of it as that line is just a copy of the real number line, right? So it can be at least approximated by just R, copy of R. So if you could do this for any point on the curve, you can draw a unique tangent so that the tangent space is one-dimensional. Then locally at each point of the curve, you're living in one dimension. So if you're an ant, let's say a person, because this is, let's say, Earth, over here, locally you think you just live in two dimensions, right? You know what I mean?
Yeah.
So at each point, it turns out we can draw a unique tangent plane. It's two-dimensional. A plane is two-dimensional. So if at each point you can draw a two-dimensional tangent plane, then locally this sphere is just two-dimensional, if you will. It's like a, so the idea is that you know how to do lots of calculus stuff on R2. So if you can do, so working on the sphere at that point should be somehow corresponds to working in R2. Yeah. Now, another thing to notice is that here this is quite obvious, but here we can think of y as a function of x, yeah? Y is a function of x. Okay. So the way that your book kind of explains this, and I would have to, did your professor not talk about manifolds at all?
Mine did.
Are you Dr. K or Dr. N?
Okay.
Yeah, all right. So, yeah, a little different. You know?
Which class are you? Account. Right, that's it. Oh.
So I won't go into the patches stuff, but no, let's do the sphere really quick. So the idea then is like in a sphere or even a circle, let's say this is the XY plane, kind of in profile, right? And this is like the Z-axis. Can we think of one of the see if you look at the upper hemisphere, can you think of one of the variables as a function of the other two? I kind of gave it away, but can you think of one of the variables as a function of the other two?
Sorry, I didn't get the question.
So at a point on the upper hemisphere, can we think of one of the variables as a function of the other two? Which one? particular works here.
Z.
Yeah. So let's just say it's a unit sphere. So we can very easily solve for Z. Now notice that Z is going to be the positive version in the upper hemisphere of whatever this is. Right, because Z is technically plus or minus. Okay. So we were able to write Z as a function of two variables where X and Y can be thought of as independent variables, right? So we call that a patch, if you will. Right. We can cover the full upper hemisphere except for the XY plane itself. So that would just cover just this part, right? And so what patch can we use for the lower hemisphere?
Negative.
That would be something. So Z for the lower hemisphere. We get that as U would be the negative. And this would work. Right? We can't think of Z as a function of X and Y on the XY plane. The graph, if you will, doesn't pass the vertical line test for a single input, you get two possible outputs for Z. So it's not a function.
Yeah.
Okay. But that's not enough because we still have, like, if you think about the equator, it's still not covered by any patch. But that's easy enough. So if you right, say if you want to cover the upper and lower hemisphere, what if you want to cover the part of the hemisphere that's facing us that has a positive X coordinate? Yeah, so for positive, so this could be this is for positive X's. Right, Z's positive, here's Z's negative. So that's the top, but we still need to cover the equator, but we can find another patch where X is, so this is the front-facing hemisphere. I don't know how to say that. Where X is positive. But we would do exactly the same thing, right? We have X, and then we have, let's say, the YZ plane. Still the same kind of profile. But now we can think of the X as a function of Y and Z. So that would be X as the positive, right? Square root of 1 minus Y squared minus Z squared. But in any case, we were able to rewrite one of the variables as a function of the other two. So the graph of this equation, if you will, or this function, gives you that front-facing patch, covers it. The idea is you have to cover everything with a patch. There could be no deletions, or you can't leave out the equator. They can overlap. And so you need, actually, how many patches would you need? 1, 2, 3, 6. Now let's see why. Because we've just covered the front-facing hemisphere. Now the back-facing hemisphere would be where X is negative, right? So X would be the negative of one approach to this. So you have the top, the bottom, the front, and the back. Have we not covered any points? Remember, this is strict inequality, right? You can't have something at the boundary because you don't get a function there.
Oh, so the upper or lower hemisphere over there, those would technically be a dome, right? Sort of a dome. Because it's an XY, not the one you colored. Yeah.
Which what color?
The yellow and purple.
Yeah, those are two separate domes.
Yeah, it domes, not just arcs.
And that didn't cover the equator here.
Right.
But now we covered the front face, so we covered this part of the equator. This is good to go. And the back part, but what we're missing is this point. We still haven't covered these 2 points, believe it or not, right?
Really.
I mean, yeah. So we need 2 more patches. Okay. So I could continue, but okay. So let's call that the left or in the right. Say the right facing hemisphere. That's where y is positive. That's easy enough, right? Y is positive, so you can just solve for y in terms of x and z. Okay. So that will cover this point here, 0, 1, 0. And so on in the left-facing patch, or the left-facing hemisphere, you can cover with a patch. So y is negative. Okay. And so you need 6 patches for at least using this idea. And they then what they make you do is do this for a donut, a torus. So, and if you need help with that, well, yeah, that's a little rougher. So if you just conceptually this will help you start, and you can come to the tutoring lab if you want some more details. But let me draw it this way. So what they do is they look at and at least in the book, they have the YZ plane. They draw a circle at some center, call that B. I don't know, which one's the bigger one? Yeah, it's called that B. And they imagine that you rotate the circle about the z-axis, right? So think, you can even think of this as the x, y plane. You're just rotating that circle about the z-axis. So you probably see what's going to happen, right? We're going to get that circle. And then once you rotate it, you get a donut. So a torus. Okay. In the xy, yz plane, this might have an equation. Let's say the cross section of that donut has a radius a, and the radius of the donut, the big radius, is b. So this equation is y minus b squared plus z squared is equal to a squared. Now this surface, obviously, locally, if you're an ant on the donut, you're living in a two-dimensional world if you're really small. So we expect this to be a 2-manifold, and they want you to find patches where you can express one variable as a function of the other 2. It's not necessarily easy, but for the top, for example, what is y? Well, what's a good parametrization of the torus? Take the points here in the xy plane. In the yz plane. So x would be 0 for now. Y would be, well, how can we get y? y would be b, if you get to the center of the circle, plus, let's call this angle theta. So if you want to get y, you would have to add cosine of a times cosine of theta. And z would be just sine of theta. Okay. And then imagine that if we take find this to be phi, I don't know what your book calls it, so but imagine a cross section here. So let's just think about it. What would add? So given a point on the circle, so for a certain phi, it's best to probably think of this as like the r plane. So the distance from the z-axis. So that would be like, this is r, r's positive, your circle. So that circle can be, I'll come back to this in a second. So we know the equation of that circle. Okay. So given a point on that circle for a given value of theta, it doesn't matter. How would you get the x component? And maybe for clarity, I'll just pick a point here just so the illustration looks better. So how would you get the x component? Well, it would be r, right?
Do we just change y to r?
So r would just be this distance times cosine of, the x component. So let me just be clear about that. Here's phi. So this corresponds, let's say that represents the x coordinate, this is the y coordinate, and this is just how far we're away, right, from the z-axis. So that's just given by the r coordinate, if you will, or the y coordinate. So this has length. So then to get the x coordinate, that would be the hypotenuse times cosine of phi. So that would be we'll get a good parametrization. So it's going to be cosine of phi, b plus a cosine theta. And this is just a standard parametrization of, like, if you go to Wikipedia, you'll probably find this. So y would be the hypotenuse times sine of phi. And then z is still just a times sine of theta. Yeah, it's kind of part of what I'm trying to explain here. I don't think I was being very clear, but the y-axis, is kind of like r because the y coordinate tells you how far you're away from the z-axis, the perpendicular distance. And so I just think of that as the r. That's this, and then just project that segment onto the x-axis using cosine and onto the y-axis using sine. That makes sense. All right.
By the way, how do we get that parametrization again? You originally had 0 and then b plus a.
Yeah, maybe I started with this because that's kind of similar to what's in your book. I would have probably started with this idea where let's just say R is the axis that represents how far you're away from the z-axis. And then pick a circle here with a certain radius A, call this theta. So in terms of theta, what is R? We're given a point on the circle. What is R? That is the distance from the z-axis. Well, it would be just B, first of all. You're starting at the origin, you got to get to B. And then you would use a cosine of theta to get that extra distance here. So that's like the radius. So let's see, that would be this, that would be, let's say, that's like R, right?
Yeah.
And then I'm just projecting it onto the x and y axes using sine and cosine. Get the x and the y coordinate. Right, so this is R, cosine of phi, according to this picture, is x divided by R. So I'm getting the x coordinate as cosine phi times R. And so on. And the y coordinate is sine phi times R. All right. So 1, 2, 3, 4, 5, 6. You're going to need 6 batches, I believe. But it's again, you're going to get the upper and lower part of the donut, and the more difficult one would be, right? So if you just choose essentially this equation, right, where R is the same thing as x squared plus y squared, maybe that would have been a better way to think about it as well. Okay. You can solve for z. And z is going to be plus or minus the square root. But so now you see that we can rewrite, and of course A has to be smaller than B, right, for this to work. So we can use this to rewrite z as a function of x and y for the upper hemisphere, so the where z is positive. That's a patch, if you will. Z is negative, and so on. It might be a little rougher too, because you're still, when you do this, you're still missing the equator. There are 2 equators in a donut, right? Well, let me just draw it. We covered the top and the bottom, but we have this equator on the outside of the torus, and then on the inside as well, if that makes sense. So we need to cover those, because these 2 patches here do not cover the equator. So that's a little rougher. But for example, we can cover the, say where y is positive, right? So that's going to be this part of the donut. Draw it. Here's the cutoff. So it's just this part of the donut here. Well, you know what I mean? Yeah. All right. Oh, crap, but not the inside. I was thinking about the outside equator. So let's just let's do one side. So let's do the equator where y is positive. and we want to cover the equator. Okay, so here that would mean that what theta is, let's say, between negative pi over 2 and pi over 2, and that's important, I guess. If I look at the parametrization. Do you see that? If we come back to the picture, if we want to cover the part of where y is positive, but we want to cover the equator, I want to cover that part. So theta has to be between negative pi over 2 and pi over 2. Draw that better. So we want to cover that part of the donut, the outside equator. The patch. So to be in that part of the donut, theta has to be between negative pi over 2 and pi over 2. Okay. And that's going to be important because then cosine of theta is positive. So
I understand we're doing the patches.
Yeah. I'm just going to do one of them. I said there are 1, 2,
Okay.
1, 2, 3, 6.
So I'm kind of confused about that one equation with theta and pi, or that
Parametrization?
parametrization. Is that a patch?
That's a great question. It's not the way your book defined it. To me, this is like differentiable. It's a function of 2 parameters. The graph is a 2-dimensional manifold. But your book did it really differently. They want you to write, it seems like, from my impression, is they want you to write one of the variables as a function of the other 2. So we're going to attempt to do that really quick.
So that's not in the book.
So that's so let's see. Notice that we can, if you look at the parametrization of that sphere, sorry, torus, if you take x squared plus y squared, what do you get? By the Pythagorean trig identity, what would we get? Right? Cosine squared plus sine squared is 1. So you get later. Have you been to the lab? If you want, have you been to the lab downstairs?
I've been to the
Tutoring? Okay. So you're aware of it? Okay. Okay. But then z is equal to a sine theta. So let's maybe square both sides. And by the way, sine is going to be positive, right? So, sorry, a is, yeah, that's right. Sine. Okay. Well, not necessarily. Okay. So then we're going to square both sides and use Pythagorean trig identity here. All right. So I'm going to solve for sine squared a squared is the same as z squared minus a squared. We're going to take the square root of both sides. But how do I know whether it's plus or minus? Well, we said that theta is between negative pi over 2 and pi over 2 if we're just trying to cover the part of the torus where y is positive in the equator.
So that's why it's plus.
It's going to be positive, right? Because cosine is positive when theta is between negative pi over 2 and pi over 2. So we're just going to take the positive version of this and solve it. So that's, all right. So then, there you go. We have x squared plus a squared is equal to b plus a cosine theta. And then if you want, you can verify, you can solve for y. Y would be, so it's right what we have. What do we have? Oh yeah, this. So x squared plus y squared is equal to this squared. So just move the x to the opposite side and take the square root. And we're going to take the positive version of that, right? Okay. So now if you want to cover the other part of the equator, where y is negative, you just take the negative version. So this is the purple patch. This is the green patch.
And that's just upper hemisphere.
Well, no, the upper and lower hemisphere, I should definitely be more clear. This is the upper part of the donut, the lower part of the donut. This is the right-hand side of the donut with covering just the outside equator. And then we have the lower part of the donut. Well, I should maybe quit here. But what if for the other side of the equator that's on the outside, you just make the y negative? Y would be negative here. Of course, I'm visualizing an XY, conventional XYZ plane, the XYZ space. But then there's the inside equator. So what would theta be for the inside equator?
It would be anywhere from pi half to 3 pi half. Or
Yeah. So this is the outside equator. This is y is negative. Yeah, and that's the outside equator. But if you want the inside equator, what would change? Well, theta would go from, let's see, we can say that for the inside equator, looks like theta, we can say, goes from pi over 2 to 3 pi over 2. And then cosine for those angles is negative. Okay, so the only thing that would change is that when we solve for, when we were over here, and we took the square root, so this time we're going to have to use the negative version. Because cosine is negative for this range of theta. So then this is going to be y is positive, but it's the inside equator. If I could spell. So that would be, let's see. We have x squared plus y squared equals to b plus this. A cosine is now negative square root. Kind of makes sense, right? Because y would now be closer to the xc plane. So we solve for y, and voila. Yeah. 1/2 squared minus x. And then for the negative, of course, or y is negative, but the inside equator, just choose the negative of that. So. So that's a long problem, but good luck finding patches. But I don't think it's, it feels like conceptually it's more important to know what a manifold is, right? An m-dimensional manifold locally at a point, you can, you have a copy is approximately like Rn, in the sense that the tangent plane is m-dimensional, and each point you have a tangent plane. Yeah. All right. I don't know if you want to get into Taylor polynomials. It's 3:15. But do you have questions? I guess I can. Something you're especially concerned about.
Let's see. I think you went further than my notes. Let's see. I think we were meant to. Let's see. So parametrization in that case.
Yeah.
With theta and phi, can you go over that again? Actually?
Yeah, that standard parametrization of it. Okay.
Yeah.
Yeah. So let's see. I press on the wrong thing. Zoomed out. Okay. So if you have a point in the xy plane, I'm only calling this phi just because some of the standard parametrization I've seen doesn't matter. That's phi. This is a point. Okay, so how do you, let's call that r for the distance between the point and the origin. All right. So what would the x and the y components be of that point? Well, x would be the cosine of phi times r, and y would be sine of phi times r. For phi, between 0 and 2 pi. Okay. So if you take any point in space, you can think of the distance that point makes to the z-axis, the shortest distance or the perpendicular distance. And that would be r. But if you're in a donut that's kind of centered, has an axis, if you will, which is the z-axis, right? If you cut this anyway, I suppose, you'll get a circle. Or I can think of this as like the r-axis. So what that looks like, you're essentially taking a plane like this and slicing the torus. That might have been a better way to think of it. Oh man, I lost my donut. Well, I guess that'll have to do. Okay. You cut that with a plane and you just get a circle. You're cutting your donut. And so what that would look like is you have the z-axis, and then you have r axis, if you will. And you have a circle. And we assume that the radius of the big radius of the donut is b. So this would be like now the smaller radius of your donut is a. And this is what we're going to call theta. So what is r and what is z in this picture? Well, z is easy enough. It's just a times sine theta. Okay. But what is r? So we're looking for the r coordinate. So it's this distance in this picture, right? That's r. So to get r, you take the length b, which is the radius, the big radius of our torus, and then you add this small amount, which we know is a cosine theta. So the r coordinate is b plus a cosine theta. Okay. So now we put it together. Right? We have x for our torus, this cosine phi times r. And y is sine phi times r. And z we already know is a sine theta. Theta and phi both go from 0 to 2 pi. Parametrization of the torus, where torus is defined by a big radius and then small radius. So that's going to be also that kind of thinking, geometric thinking is also going to be useful when you look at spherical coordinates, right, if you haven't already.
When is the session?
Hmm?
When is the session?
Oh, it's over. It's been over. Since it's 3:15.
Oh, I see. Okay. Thank you very much.
Sure.
Yeah.
Even though it was we didn't cover very much, you know. All right.
I think it's just the nature of the subject.
I think so too.
It's better than nothing.